Hey guys, in this sequel of videos, we'll go through the step in creating a graph neural network and apply it to existing datasets. First, why do we care about graph machine learning? To me, graph can represent most of the data structures. For example, social networks like Facebook, Twitter, and LinkedIn are huge graphs in which nodes are users and edge is a connectivity between the users. For example, when the two users are friends. Another example can be um, in natural language processing. The attention mechanism in NLP computes the tension between any two words in a sentence. So if we view each sentence as a graph, then each word can be viewed as a node, and any two words are connected by an edge. In this case, we have a special graph called complete graph because any two nodes are connected by an edge. In dealing with graph, we only want to compute the computation based on the graph structure. For example, a node should only be affected by its neighbors. In a single update, its features will only use the neighbor feature for the update. The DGL framework is a framework that regulates the feature update based on the underlying graph structure. So in this video, we will first discuss graph convolutional network, which is almost identical to the NN dot linear layer, with the exception that the computation is done based on the graph structure. If you haven't installed DGL, so you will need to install DGL to be able to follow along. And here are the dependencies that are needed for the installation of DGL. You can also look at my other video for the details. You need to install this dependency and install pip install DGL. So let's go to the first notebook here. Let me turn off this screen so that it will not interfere with the notebook. So first we will import necessary package, and I want to talk a few words about the diffgraph library. So DGL integrate built-in function which allows us to compute feature updates based on the graph structure. To simultaneously update all the node features or all the edge features, the following three functions are used. First, message function is a function on the edge in which each edge has three attributes: the source node, the destination node, and the edge feature, which is data. What this function does is that it sends the information from the source node to the destination node. So this function will return a dictionary that stores everything needed to do the node feature update in the update equation. This dictionary is called mailbox, and this mailbox can be accessed via nodes.mailbox. After we call the message function, we will call the reduce function, and this is a function which takes nodes as argument. So this function implements the node feature update equation. All the information in the mailbox, which is obtained from the previous function, will be used for the update in this function. And lastly, we call g.updateAll, which take in the message function and reduce functions, which simultaneously combine these two functions. So basically what it does is it sends message to all the edges and update features of all nodes at the same time. Additionally, if we want to update feature of the edge, we can use the function apply edge. So the dataset that I am going to use for this notebook is the cora dataset. This is a single graph of citation network. So the nodes in this dataset are papers, and the edge are connectivity or the citation between two papers. That means there is an edge between two nodes if one paper cite the other paper. So first, let's load the dataset and inspect the property of the dataset. So dataset here is dgl.data cora graph dataset. This is a dataset with one graph, so we can also extract the graph here. and let's print out the graph as well. So here the dataset has 2,708 nodes. There are about 10,000 edges, and we have other information about the feature dimensions, the number of class, and the training, validation, and the test samples. For the graph in this dataset, it has 2,700 nodes, about 10,000 edges, and the feature dimensions of the node is 1,400. And we have other keyword here, like label the mask for chain test and validations. So here I'm going to use this graph, and I will illustrate how the GCN works, the graph convolution network work. So as mentioned earlier, GCN is almost identical to the usual NN dot linear, with exception that it is done based on the graph structure. So here is a simple case that I want to discuss before we dive into the details of GCN. So the purpose here is to get used to this framework where we update the node features using the message function, the reduce function, and the update all. So in this simple case, assume that we have one single layer in which the update equation is that each node feature will be updated to be the mean of the features of its neighbor. So hi here will be equal to the mean of hj for all the j here are neighbors of I. So ni here means all the nodes j that send information to the node I. So ji is an h, j is the source h, and I is the destination h. So in this case, we want to implement these equations. So we are going through three functions: message function, reduce function, and update all. The message function needs to store the information that is needed to implement this equation. So basically, it will store all the neighbor node features. For the reduce function, we simply take the information that is output by the message function, which are all these neighbor node features, and then we take the mean of these neighbor node features. And update all here is just a simple call function on these two functions so that it performs both message function and reduce function simultaneously on all nodes. So let's implement this with the graph, with the cora graph, which we just loaded. So let's go to the code here. Now I need dgl.function as fn. So let me call this single layer min layer. It also sub module the nn.module. In this case, we don't have anything to do the init for the self, so we simply do message function. So message function here take in h as argument. We will have reduce functions which take in nodes as argument, and we have the forward. So in the forward function, that is where we do the update all, which take in message function and the reduce function. Now we will fill in the detail. So in the message function, note that the argument h here will consist of the following informations. So h here consists of the source node, destination node, and the h features, which I call data. So in this case, we want to extract all the features of the source node. So we will extract source node features. Let's say sorry, it should be H. We take out the source node, and here assume that the feature are stored in the keyword H. We are going to return a dictionary in which the message that we want to pass from the source node to the destination node is just the feature of the source node. So these are the HJ here. Now in the reduce function, we want to do two steps. So note that in the reduce function, we want to implement these update equations. So first, we will need to extract all the HJ that are stored in mailbox. So this just now are stored in mailbox. So extract neighbor node or neighbor node features from mailbox. So we simply take m equal to node dot mailbox m. Note that this mailbox has key m. So when we return this, which means we return the mailbox. And now we simply return a dictionary. Let's say the new updated features is hn, and this is the mean of the neighbor node along the first dimension, along the second dimension, dimension 1. The first dimension is usually the batch dimensions. So next in the forward functions, well, we need to take in the graph and the input node features as argument. So G here is a graph and H here is the input node features. Now we want to compute, to have the computation only on this graph G, so we would use with a local scope. So first we are going to assign the keyword H to the input feature H, and we will do the update O function in which we send the message through the H, and then we update the node features through the reduce function. Once we do this, we get the dictionary here, in which now hn is the updated node features. So we simply need to extract the value hn here and return it. So we are return hn. Note that the features of node feature of G are stored in g.ndata. So when we return this dictionary, which means node features, they will be stored in g.ndata. Right, so that is, yeah, that's it. Well, this is supposed to be fn. It is not basically not needed here. All right, so now we are going to see, let's say, how this works, apply this on our cora graph that was already extracted above. Let's say we want to see how the feature of some node change, let's say node 0, features before the update, and we want to print out the feature after the update. So before the update, we can print out the features via g.ndata of the node zeros. So here I think I might have gone through a little fast here. So in the graph G here, the end data consists of all the node features, and this graph has no H features. The node here Each feature is a vector of dimension 1433, and each node has a label, and we have the marks, validation marks, test mark, and chain marks for the node. And in order to access the feature, we need to access via the keyword fit. So this is the feature of the first node before the update. And now we want to compare the feature of this node after the update. So here we need to have this layer, mean layer here, and we want to extract out the feature of all the data. Note that in the forward function we need G and H, and H here is the input node features. Okay, output now will be layer GH. We can print out the shape of the output. It should have the same shape as the shape of the G.N data feature here. Okay, so we can also print out the shape of G.N data and compare it with the output shape. They should be the same. And now we want to see what is a feature of the node 0 after the update. So we will print out 0, and we want to compare this with the original feature. Super has no in, super init. All right, so here is the result before update. This is the features of the node 0. After update, well, here are the size before and after update of the features of all the nodes. And after update, you can see that after update, the node 0 should have feature as the average of all the neighbors of the node 0. So it should be different from this. And based on judging on this entry, we can see that the update is taking the effect here, and this is the average of all the neighbors of the node 0. And now we will be implementing graph convolutional network layer from scratch. So in GCN, the update equation at each node is computed as follows. So here we will take sum of the neighbors with some scaling constants, can be weighted sum of the neighbors, and then apply a linear transformation on this weighted sum. So W and P here are seen with the matrix, and the weight and the bias in these linear transformations. So in this case, there are a normalization constant Cij. Cij is the normalization constant, and its value is equal to the square root of degree of j times the degree of I. And this single equation can be done via this built-in function, graph convolution in feature and out features. However, we will implement this equation from scratch using the concept of message function, reduce function, and update all. After that, we will also use a built-in function and then compare the performance between our function that is coded from scratch with the built-in function. Well, so here, let's start the block of code from here. So we want to have a GCN layer we will init this with the input dimension and the output dimension. So for this equation, we need to perform a linear transformation on this weighted average of the neighbors. So self.linear is nlinear from the in dimension to the L dimension. Here I'm trying to match the official code for this GCN layer. So in this official implementation of the GCN layer, we need to initialize the parameters by the Xavier's initializations. We will initialize the linear layer here by the Xavier's initialization. The weight are initialized by the Xavier initialization. So here I will have an init weight functions that is written below. Here we only have one module, which is the linear module, but we still check do this, so it will work in any case. So if we have a linear module, we will init it by Xavier uniform for the weight. For the bias, we want to init it to 0. So whenever we call this module, we will apply this init method. So now we are going to implement this equation here. So here note that G is the input graph, and H here is the input node features. We want to compute within the graph G, so we use with G dot local scope. In fact, in this case, I'm going to use some built-in functions to implement this. So I will tell you exactly what that function is, because what I need in this case here is simply to take the sums of all the all these terms, and there's a simple built-in function which can take the sum of all the neighbor features. So there is no need to code what is the sum of the neighbor features via the message and the real function. So here, what we need is we need to compute the normalization constant Cij, which is the square root of degree of j times degree of I. So first, I will need to extract the degrees, all the degrees of the graph. So to extract all the degree, we need to use the in degrees, and let's cast this to float type. And here, the normalizations of the degree is just 1 over the square root of the degree. So we will take 1 over the square root of all the degree, and we will unsqueeze the last dimension. Next, we are going to normalize all the node features. So we touch dot unsqueeze. Next, let's normalize all node features. So by doing this, we have just update node feature of node hi to hi divided by its degree, square root of its degree. So here I will multiply h by the normalization constants. So in doing this, the multiplication is done element wise. So hi is now equal to hi divided by the square root of its degree, and we will assign new node features. So g dot and data h, now we assign to h, which is a normalized node features. And next we will update new feature for h to be the sum of all neighbor features. So new features for this key h here will be sum of all neighbor features. Well, in doing this, what we will get is that we have each node, for each node I, hi will be the sum over neighbor j of hj divided by degree, square root of degree of j. Why I am doing this? I am doing this because later I can, I am almost finished here. If you look at the equation here, if I do this, then I get this hj over the square root of degree of j, and all that remains is to multiply this by the square root of degree of I. And this can be done by pointwise multiplication with the norm, with the normalization constant, which I call norm here. So here we will do it via g dot update o. So note that in g dot update o we need to pass in the message functions and the reduce functions. The message function is a function in which we need to store the informations from that will be sent from the source node to the destination node, and in the reduce function we use the store information to do the update equation, and the update equation we want here is simply the sums. So the information that we want to send will be the features of the neighbor nodes, and in this case all the neighbor nodes already have feature hj divided by degree of hj because we already did this step above. So I will send the feature h of the source node, just copy it to another feature m and send it to the mailbox. For the reduce function here, okay, sorry, so this I should have a built-in function that is copy u, that means copy this feature h and create a feature m to store in the mailbox. For the reduce function, we will take the sum of all these send feature, all the feature in the mailbox, and we want to update the node features, so we will store it in the keyword h here. So after this, now all the node will have feature equal to the sums hj over the square root of degree of j. All that remains is to multiply this sum by the normalizing constant for the node hj. So next step will be to normalize by degree of the node I. So the output here will be g dot and data of h multiplied by the normalization constant. And finally, we will do perform the linear transformation. So out equal to self linear out. We will return out. So yeah, that's it for the GCN layer. And let's say we want to apply this layer to create a model which consists of sequence of these layers for the classification problem. So, well, here first let's create a model. Let's have another block of code here. In this model, I will have a simple model in which we take in the input, we pass it, let's say we pass it through two GCN layers, GCN1 with some activation, let's say ReLU activation, and we pass to GCN2 and use the result of GCN2 for classification. So let's implement this model. Well, we need the input dimension, we need the hidden dimensions, we need the output dimension, which is the same as the number of classes. So again, note that in this cora graph dataset, there are 7 classes for the nodes. So we need the super init. So here there are two GCN layer. Maybe yes, GCN1 is GCN layer which take in the input dimension and map to the output dimension. The second GCN layer will take in the hidden dimension and map to the output dimension, which is the number of classes. So now we will define the forward function. So we take in G and its features with G dot local scope. Well, so here we will pass the feature first through the GCN1. So let's say H equal to self dot GCN1 G features, and we will do a ReLU here on the H, of course, and we will pass it to GCN2 and we return H. So the output here will be the nodes with dimension, node features with output dimension number of classes. Well, we can create a model, a sample model here, and just see the property of the model. So GCN model, which take in, let me go back here to confirm the input dimensions. So input dimensions in this case is the input, the dimension of the input features, that is 1443, and the output dimension is the number of class, which is 7. So let us set some hyperparameters here first. Well, let's just do this in the next block. So in dimension is G dot and data fit dot shape -1, and num classes dataset dot num classes. For the hidden dimensions, what would be the hidden dimension we should use? Let's try the hidden dimension to be 1 to 8. And now we will create the model based on these parameters. And let's print out how many parameters are there in our model. Let's print them in terms of million of parameters. And let's do one forward pass. Let's say the G is so in forward pass we have the G and we need to extract the features. So out equal to okay, let's touch dot know what out is net G features. Well, let's print out the shape of the output. Okay. Mistake here is GCN layer have no attribute init weight. So something is wrong with the weight initialization. So this is just one underline. Type, should I need this? Argument input position 1 must be tensor. This need to be tensors. So well, let's check what is the data type. I guess the features here are not tensors, so we need to convert them to tensors. But first, let's check type of the features. They are tensors. Should be tensors. Unsqueeze. So oh, it should be it is not. It's not because of the one just now, but it's because of the norm that I unsqueeze so I can do the pointwise multiplication here. So I should have unsqueezed. I didn't indicate what I unsqueezed. So maybe here let's use norm dot unsqueeze. So now GCN layer missing is H. It shouldn't. So here we have GH. Okay, so yeah, GCN2 here, we don't have G. All right, finally, we make it work. So here, our model have 0.18 million parameters, and the output, here the output shape, indicating that there are 7 classes. Now we are going to do the train and the evaluation function for the node classification of the cora graph dataset. Well, first let's check out the train mask, the validation mask, and the test mark. These are simply the Boolean indices for train, validation, and test. Train mask here can be extracted from n data. Validation and test can be done in the same way. And let's print out how many nodes are there that are used for train, test, and validation. So train node. Because these are Boolean values which are 0 or 1. So to get the total number of nodes, we need to take the sum of them. We do the same for validation and test. Something, oh, so this should be validation, it should be test. So we can see that the number of chain nodes is 140, validation node is 500, and 1000 nodes are used for testing. So now we are ready to write the train and the evaluation function. In the train function, we take in the model, we take in the graph, we take in the loss function and the optimizer. First, we put the model to train mode. We extract the features of the graph. We extract the label as well. We do forward and backward. Here, in case I always forget this, we need to zero grad the optimizer. First, we do the predictions on the whole graph. And from this prediction, we will extract out the prediction on the chain nodes. The prediction on the whole graph, I could logits, because our model produce logits. So we take in the graph and the features. The loss will be computed only based on the chain nodes, which are chain mask. Can be extracted. The chain nodes are extracted from the chain mask. So loss here equal to the loss function computed on chain node. Label here should be label of chain mask. Chain mask already extracted above. Now we do the backward, loss backward, and optimizer step. So we also want to compute the accuracy. Let's say prediction here will be the logits, the position of the logits with the highest value. So we do the argmax. Accuracy in this case, so we want to compare how many predictions are there, match the actual label on the chain mask. And we want to take the mean of this. So here, to take the mean, we will first convert this to float and take the mean. And so here we return the loss and the accuracy. So this is one single epoch. Not sure why there is this red here, but do I miss out? Okay, so this is the error. So that is the train functions. For the valuation function evaluations, first we set the context to not to check the gradient. We put the model to the evaluation mode. We check out the features. And we extract the labels. We do forward. Well, for evaluation, we don't need the optimizers because we only want to compute the loss and compute accuracy. In forward, we compute the logits. and we compute the loss. Loss function in this case will be performed based on the validation mask. And then we also want to have accuracy. So the prediction on the validation node. First, we extract the prediction for all the nodes, and we compare the predictions on the validation node with the labels of the validation nodes. We take the mean of them. Then loss and accuracy. Yeah, that's the train and the loss functions. So accuracy, this should be comparisons. All right, so now we have the train and the loss function. We are ready to train our model. So let's set a random seed here for reproducibility. We will set this to change on, maybe to be safe, to take not too much time, just 30 epochs first. Even though this should be fast because our model only has 0.18 million parameters, which is quite small. Let's initiate the model again. So we take in the in dimensions, hidden dimensions, and the number of classes as the output dimension. Also want to print out the number of parameters in the model. In million parameters. The loss function we want to use will be the cross entropy loss, because we have 7 labels. Optimizers will be AMW. AMW is improved versions of ADAM, and it usually converges faster than ADAMs. Learning rate here, let's put 0.1. We're training for only 30 epochs. So now we go through the train and test loop for epochs in range number of epochs. We'll run the train function, which take in model. The graph is the graph G, loss function, and optimizers. And then the validation loss and accuracy. Evaluate the model on the graph and take in the loss functions. Let's say here now we will print out epochs. So we want to print out everything's chain loss. Let's print it to 4 decimal places. Want to print the train accuracy. So let's print it out in terms of percentage. And we do the same things for for validation. Validation loss, validation accuracy. This is percentage, not star. That seems to be it. Let's run this. Alright, so it runs quite fast because our model is quite small, and let's see when we get to the loss zeros. So here after 25 epochs, the loss is 0, and the validation accuracy is 77.6%. Now we will build our model from the built-in GCN layer. Here is a syntax for the built-in GCN layer. We need to pass in the dimension of the input features, dimension of the output features. Normalization equal to both here is a default. So that means this normalization means a constant Cij that appear in the formula, and the rest are just some default parameter. To recall, our model take in the input, pass it through the GCN layer 1, apply a redo activation function in GCN layer 2 and take the output for classification. So let's define a GCN net. Well, this is a markdown. I need to have a code block. Here we will init this with the in dimensions, hidden dimension. Output dimension is the number of classes. So we also have two GCN layer, GCN 1. Well, let's import this from dgl.nn import graph convolution. So we take in the in dimension, output is the out dimension. For GCN2, we map from hidden dimension to number of classes. So here we forward the graph and its features. So first we pass the features through GCN1, and we use redo activation functions, and then we pass it through GCN2, and we return the features. So now we will load the model and do it to the train. Let's say model 2 GCN net, which take in the same in dimension, hidden dimension, and number of classes as before. Let's spin out the number of parameters to make sure that we have the same number of parameters as the previous model. P in model 2 dot parameters. I want to print them out in million parameters. The set loss function to be cross entropy optimizer the same as the one just now, AWW, and same learning rate. Let me check again to make sure that we are using the same thing. Yeah, learning rate 0.1. Now we will do train and test. Let's just copy the code that we already write. So here we train on model 2. Now let's see how the training works. Relu miss one input, so it should be relu here. All right, so yeah, it is done in, the training is done in 0.4 seconds. So here we can see this model has about 0.18 million parameters, exactly the same as the model that we coded. It let's see, at epoch 21, so the training here, we get down the loss 0 at epoch 21, so it's faster, a little faster than the model that we coded. I am not sure of the reason. I try to match everything to the original GitHub for this model, but here we can see for the built-in model, it go down to the loss 0 at epoch 21, which is a little better than ours. But ours works just almost the same. So in summary, in this tutorial, in this video, I have gone through the details in creating a graph neural network, in which we have 3 important concepts to update the node features in a single layer. These concepts are message function, which is used to pass the information from the source node to the destination node. These information will be stored in a dictionary called mailbox. The reduce function is used to update the node feature based on the update equation. So we will use the information in the mailbox to update the node features. And finally, the built-in function update all here will implement the message function and the reduce function at the same time on all the nodes and the edge of the graph.